So the two lectures tomorrow will be delivered using the slides. So let's start with the topological quantum chemistry in one-dimensional system. So basically, this topological quantum chemistry theory gives us a very simple and quick method to diagnose material is topological or not. So the simplest example starts in the in 1D system. So I will show you that it's really very simple. It's much simpler than the notion of barrier curvature, barrier connection, and the chain number, and so on. So basically, what we are making use of is only symmetry. So we start with a 1D system with oh, sorry.
No, it is. But it looks like when.
Maybe.
Yeah.
Okay. Maybe I can just use that whiteboard.
If you don't move this, I think.
Okay.
Well, we can try.
Okay. Okay, sorry. Okay.
It's not work. Yeah. Can you unplug it again?
Okay, sorry for this. So we start with a 1D system with a symmetry group generated by translation and inversion. So I first introduce this SAGE notation for spatial group element. We denote a symmetry element by this notation. So basically, this PG is a point group operation. It can be represented by a 3x3 matrix, and this TG is a translation vector. So if you apply this G operator to a position R in real space, it sends this R to this PG times R plus TG, right? And all these operations written in this form can form a group. So when you multiply two elements in this notation, you obtain their product in this row. Okay, so following this rule, these operations can form a group. So the system now we are considering has only two symmetry generators. We denote them as the translation Tx. This one is just identity, and it has a translation of unit length in the x direction, and the other generator is the inversion symmetry. So this -1 is just the inversion, and it has no translation vector. Okay, so now let's consider the lattice structure in real space. We can plot the 1D lattice structure in this way. So this is 0, 1, 2, 3. And in the middle of each unit cell, we put another notation cross. Yeah. And now let's consider symmetry of all these different positions in real space. So we can first notice that all the integer positions are actually have higher symmetries than points in their neighborhood. So for example, the position located at x equal to n is invariant under this operation. So we can verify this immediately. When we first apply this -1 to this x, then we get -n, right? Then we add this number by 2n, so we go back to n. So it's invariant under this operation. And this operation can be written as the inversion followed by a translation of 2n times, right? And the other set of high symmetry point is the half integer positions. And it's directed to verify that all these half integer positions are invariant and operations like this. So basically, it's P followed by Tx to an odd number, right? Okay, so now we can introduce the notion of Wyckoff position. So we notice that at each unit cell we have two high symmetry points. we label this integer position. We give this integer position a notation as A, right? It's just a notation for the Wyckoff position. Wyckoff position basically means labels all the points with different symmetries. And the other is the half integer position. And we label this position as B. And the third one is the general position. So if we have a general position at between 0 and 1/2, then due to inversion symmetry, we must have a partner at 1 minus x, right? So for this type of position in each unit cell, we have 2. So we label this as 2C. Okay, so after we classify this, fine. How to add a new page? Okay, thanks. Okay, so after we classify all these high symmetry points in real space, we can talk about crystals and insulators. Basically, we can understand a crystal. We can understand a crystal as a realization by occupy all these Wyckoff positions by different atoms, right? And in this point of view, one can define an insulator. I think Zach gave a very interesting definition for insulator in this framework. He said that a band insulator equals to a band representation. What's a band representation? Band representation, mathematically, it's a reducible representation induced by irreducible representations at the Wyckoff positions. We can express this in a more intuitive language. So that means we put some local orbitals at all these Wyckoff positions and add their symmetry partners. So Zach defines such a thing as a band insulator. And later, basically, the work by Andre and the work by Ashwin find that this definition is actually wrong. And it's very interesting that all the topological insulators can be understood as a counterexample to this definition. So in the following, I will show you how this definition works. So we continue our 1D example. Let's consider how many band representations can be found in real space. So basically, we have 2 high symmetry positions, the 1A position and the 1B position, right? And each position has an inversion symmetry I just explained. And for at each site we only have 2 types of orbitals. That is the even one and the odd one and the inversion symmetry. That means that at each site we only have 2 IREPs. So we label the even one by AG and the odd one by AU, right? So counting this, we find there are only 4 possible local orbitals, or equivalently band representations in real space. These are all the possibilities we have in real space. And now let's transform these real space orbitals to momentum space and see what we can say about the band structure. So now let's denote a local orbital in real space by this notation, R alpha. R denotes the unit cell. It's an integer number. And alpha takes values in AG at 1A, AU at 1A, AG at 1B, right? And AU at 1B. So alpha takes 4 different values. And with this local orbital defined in real space, and we can apply a Fourier transformation to obtain block basis in momentum space. This is very direct, actually. The only subtle thing here is this T alpha vector. For alpha for alpha being local orbitals at the 1A position, this T alpha is just 0. But for the orbitals at 1B, it's 1/2. It's just the location of the local orbitals. So T alpha here is 0, 0, 1/2, 1/2. But this phase factor is very important. It determines some very useful inversion eigenvalues in momentum space. So we must take care of this phase factor. So now let's see what inversion can do for this block basis. Now let's try to apply inversion operation to this block basis. And in the first line, we leave all the numbers, all the factors invariant. And this P only act on the local orbitals R alpha. Okay. So we denote the transformed state as alpha prime, R prime alpha, Kc alpha. So Kc alpha equals to 1 or minus 1, depending on the parity of the local orbital. So for all the AG orbitals, Kc alpha is just 1. For the AU orbitals, it's minus 1. And this R prime is another unit cell satisfying this relation. So basically, the P operator has two actions here. The first action is to give a phase factor Kc alpha. The second action is to transform this local orbital to some other position. And we can substitute this relation back to this phase factor, and it's very simple to derive this relation. This is quite direct, right? And now something important will happen. So let's consider K. We only have two inverse invariant momentum, right? The zero momentum and the pi momentum. So if the momentum is 0, then it's fine. The minus sign here is nothing, right? Because K is 0. So in this case, we have the conclusion that P times K of phi K alpha just equals Kc alpha phi K alpha, right? So this is simple if K is just 0. But if K is pi, we notice that minus pi does not equal to pi. There is a 2 pi difference. 2 pi is usually regarded as equivalent to 0, but it does not equal to 0. And that 2 pi phase factor will matter if we consider this T alpha vector, right? So if K is pi, we will have this result. Kc alpha times e to the I 2 pi T alpha phi K alpha. So we have this additional phase factor. And this phase factor is quite simple. It's just 1 if alpha is an orbital at the A position, right? And it's minus 1 if alpha at the B position, right? So now let's do a mapping between the momentum space and the real space. So remember that we have this, we have these two eigenvalues. At the gamma point, or K equal to 0, we have the eigenvalue Kc alpha. And at the pi momentum, we have Kc alpha multiplied by this additional phase factor, right? And so now let's make a table for all the possible local orbitals in real space. It's AG at A, AU at A, AG at B, and AU at B. And K equal to 0, K equal to pi. For AG so for K equal to 0, the phase factor, the eigenvalue is just the parity. So we have a plus sign here. And for the orbital at 1A, the two eigenvalues at 0 and pi are the same. So we have plus plus and minus. But for the orbitals at the B position, there is a phase difference between the two eigenvalues. So basically, we have plus minus and minus plus. So this is very simple. But this mapping tells us a very important thing. So, explain what's the question? Okay. So basically, at k equal to 0, it's run out of charge, I think. The pen is running out of charge, I think. Maybe I can use that whiteboard. Okay, so for now I use this. So basically, we at k equal to 0, the eigenvalue, the p eigenvalue, is just C alpha, right? And C alpha is a parity of the local orbital in real space. But if k is pi, then the eigenvalue is given by this C alpha followed by a phase factor e to the I 2 pi times T alpha. Okay, so for the table I just show here, in the first line I just put C alpha. So C alpha is just the parity of the local orbitals in real space, because we are at the 0 momentum. In the second row, I show the eigenvalues at the pi momentum. So what I put is just this factor. So compared to the first row, we have this additional phase factor, right? Does it work now? No?
9%.
Okay. Okay. So this mapping is simple, but okay. Thanks. Okay. So this mapping is simple but very useful in the sense that imagine now we are doing DFT calculation and we have a band structure, a 1D band structure, and we know nothing about the wave function of this band structure. The only thing we can do is that the simplest thing we can do for this band structure is that we can calculate the eigenvalues, inverse eigenvalues for this 1D band. So imagine that we have one band and we have inversion eigenvalues like this. For example, in some DFT calculation, we have this band structure. And according to this mapping, we can immediately know that it's AG at 1B. So it's even orbital locating at the 1/2 position of each unit cell. So you can see that from this table, you can read out the polarization of this one band structure. So if you have some knowledge of the polarization theory of electronic band, you maybe know that this polarization is given by the pi-Barry phase. So basically, this is saying there is a constraint between the pi-Barry phase and the inversion eigenvalues. And sorry. Okay. So basically, from this example, we can understand that there is a constraint between the inversion eigenvalue and the pi-Barry phase. Basically, we can have this with inversion symmetry. The Barry phase, let's denote the Barry phase as theta over 2 pi. Theta over pi minus mod 2 equals to n gamma minus plus nx minus mod 2. So the first quantity is just the Barry phase. So with inversion symmetry, theta is either 0 or pi. It's quantized. And in the second row, n gamma minus just counts the number of all the levels at the 0 momentum. And nx minus just counts the number of all the orbitals at the x momentum or the pair momentum. So basically, we can derive this relation. But in 1D without particle Hall or chiral symmetry, there is no true topological insulator or topological superconductor. So basically, even though we can know this non-trivial Barry phase, all these insulators are topologically trivial. And in Zach's original paper, he analyzed this 1D example and see band insulator is band representation. But counterexample starts to appear if we move to 2D. In 2D, this one-to-one correspondence in real space and momentum breaks down. Now let me show you the counterexample in 2 dimensions. TQC in 2D. Okay, so now let's count let me give all the symmetry generators in 2D. First, we have the translation symmetry along the x direction, right? And then we have the translation symmetry along the y direction. And then we have the inversion symmetry, -1, 0, 0, 0. It's a trivial generalization to the 1D case. And similarly, we can decompose the cell according to the side symmetry group. So now let's plot a unit cell in 1 dimension. Now we have 4 high symmetry points in real space. We label them as 1A, 1B, 1C, and 1D. All these points in real space are invariant under some inversion symmetry, just like in the 1D case, right? This is the real space cell. And the brilliant zone also has 4 high symmetry momenta. It's the gamma, x, y, and m. So we can know that there must be a counterexample by simple counting. Now let's do this simple counting. Imagine how many band representations we can have in real space. So first, we have 4 choices of site, A, B, C, D, right? And for each site, we have 2 choices of orbitals, the even one and the odd one. So the number of band representation of EBR, here E means the elementary. It means the minimal band representation. So the number of EBR is given by 4 times 2. 4 counts the number of sites, and 2 counts the number of orbitals you could have. So in total, we have 8 different EBRs in real space, right? Now let's imagine how many possible band structure we could have for one band in momentum space. So consider a one band. We have 4 different high symmetry momenta. And at each momentum, we have 2 possible parities, either even or odd, right? So how many possible band structure? It's given by 2 to the 4, right? So at the gamma point, we have 2 choices. At the x point, we have another 2. So 2 times 2 times 2 times 2. So it's 16. So obviously, we have more choices in momentum space than in real space. So there must exist some one band that cannot be interpreted as a local orbital in real space, right? So let's imagine we could make such a band. So there are still possible 2 options. So let's consider there is let's say it's exceptional band, right? Exceptional band. So there are still 2 options. So first, this exceptional band could be gapless, right? So it's only gapped along this high symmetry line, but it may have some Weyl points or Dirac points at some other positions we do not see in this band plot. So it could be gapless. So if it's gapless, then Zach might be correct in this setup, right? But it could also be gapped. If it is gapped, then Zach's observation is wrong. And but it's very interesting that now we must have a new phase, right? A new phase that is not local orbitals in real space. So now let's analyze whether this exceptional band could be gapped or gapless. So following the calculation in the 1D case, we can make a table for all these EBRs. I won't write all of them down, but I just write a few columns. So gamma, X, Y, M, A, B, and so on. So I will only write down the first two columns. For the even orbital at the 1A position, all the parities at this 4 momenta are positive 1. And for this odd orbital at 1A position, all these eigenvalues are -1. So the remaining columns you can find on the Billboard server, right? I don't have to write them down explicitly, but I can tell you a simple rule for all these parities. The simple rule is that this Xi for all these possibilities, this Xi gamma, this is the parity, times Xi x times Xi y and times Xi m equals to +1. This is very simple. If you just do this mapping one by one, you can immediately observe this rule. So now let's consider how an exceptional band can happen in a band structure. Let's consider we have band structure like this. We have gamma x y, gamma x m y, so plus 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 plus, and minus 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 minus. So at the beginning, it's obvious that the lower band corresponds to the even orbital, and the upper band corresponds to the odd orbital. So they could be the EBR in real space. They could be local orbitals. Now let's consider to create a so-called band inversion that interchange the two levels at the gamma point. So after this band inversion, we could have minus plus 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 and plus minus minus minus, right? So the question is this. So if we do this, the lower band becomes the exceptional band. So the question is whether it's gapped or gapless. So we can answer this question by writing down a simple KP model. So let's consider this band inversion process. So at the other points are at a higher energy, we only focus on the states around the gamma point. So at the beginning, we have band structure like this, right? Minus, plus. And we make the band inversion in this way. So let's model this process. So the only constraint for this model is the inversion symmetry. And we choose to write the inversion symmetry as sigma z. Sigma is a Pauli matrix. And the Hamiltonian should follow a simple rule as this. So basically, sigma z is the inversion operator. It should send k to minus k, right? And then following this constraint, we can write a KP model like this: m times sigma z plus d1 k sigma x plus d2 k sigma y, right? And this m can be a function of k, but for simplicity, we just assume it's a constant. It's invariant under the inversion. And following this constraint, we immediately know that D1 and D2 are odd in K, right? Odd in K. So when K is 0, the Hamiltonian is simply m times sigma z. And the band inversion is realized by the changing of sign of m, right? So now let's see if the total Hamiltonian is gapped or not. The simplest choice for the D1, D2 function is just the kx and ky. So the simplest Hamiltonian we could have is m times sigma z plus kx sigma x plus ky sigma y. This is the simplest realization of the Hamiltonian I just mentioned. And it's quite easy to find the energy band is just this, right? It's just this. It's a Dirac Hamiltonian. So obviously, as long as m is non-zero, we have a gapped phase. And actually, now it's not surprising that actually this exceptional band is gapped, and actually it's a chain insulator. I don't have time to go detail to prove why this is a chain insulator, but the simple idea is that when we close the band gap of a Dirac equation, we can calculate the Barry curvature around this gap closing point, and we can prove that the change of the chain number before and after we close the gap is 1 for this Dirac Hamiltonian. And we also know that before we close the gap, the lower band is simply a local orbital in row space, which must be topologically trivial. So we know that so after the band closing, the lower band, the exceptional band, must have chain number 1, right? And if we do more detailed analysis, actually we can prove a very useful constraint between the chain number and the inversion eigenvalues. The constraint is given by this -1 to the C. C is the chain number of an insulator. E is constrained by this expression. Here K goes all the high symmetry points in the system. It's gamma, X, Y, and M. And N goes over all the occupied band. And C, K, N. This is a parity of the nth occupied band at the momentum K. So this can be proven mathematically. The basic, I don't have time to prove this in this lecture, but I can give the basic idea for this proof. So basically, we can consider the integral of the Barry curvature on half of the Brillouin zone. So we consider the Barry curvature in this half square, and this quantity is also given by the line integral of the Barry connection along this path, right? And the interesting thing is that this path passes over all the high symmetry points, the gamma, X, Y, and M. And so you can analyze the Barry connection at different segments. And this Barry connection at different segments are related by the inversion symmetry, right? They are not independent to each other. And when the inversion operator relates the two segments, the parity of the occupied bands will enter this problem. And through that analysis, sorry, it's here. Okay, sorry. So by this analysis, it's not very hard to prove this constraint. Okay. So basically, this is simplest example for symmetry-based indicator. We call it an indicator because it's not the full classification of the problem. For this 2D system with inversion symmetry, the topological classification is still Z, but this indicator is just a Z2 number. But it tells us some very useful information about the topology. So in the next, I will talk about the general structure of symmetry-based indicator. And then if I have more time, I will go through a 3D example. So structure of symmetry-based indicator. So given the examples I just talked about, it's reasonable to say that a description of a band structure can be given by the multiplicity of occupied irreducible representations. So we can introduce a vector we call it a B vector in this way. Sorry, K1 row 2, MK2 row 1, MK2 row 2. So let's explain it. Let me explain this notation. So Ki goes over all the high symmetry point in Brilliant zone, high symmetry momentum in Brilliant zone. And this row I, row 1, row 2 are all the possible irreducible representations at the corresponding momentum. So I write it as IREPs. In the example of inversion symmetry, row 1, row 2 is just the even or odd representation, right? But in some other groups, row can be much more complicated. But anyway, it's just the representations of groups. So this M counts the number of occupied row representation at the momentum K. And so we tabulate all these integers and we make it a vector. We call it the B vector. So this is a very simple description for a given band structure, right? It's not a complete description, but it already can give us a very useful information. And this for the band structure to be an insulator, this B vector must satisfy some constraint. For example, in the let us go back to the 2D example. In the 2D example, it's clear that we must have these constraints. M gamma plus M gamma minus must equal to X plus X minus. This is a very trivial constraint because at every momentum we must have the same number of occupied bands, right? Otherwise it cannot be an insulator, right? Y plus, I won't write down all the constraints, but you understand this. This is just the constraint on the band number. But in a more complicated symmetry group, there are more constraints than this. For example, the levels along the high symmetry path must follow the so-called compatibility relation. So let's consider two high symmetry points, K1, K2. Let me write them as K and P. So these are two high symmetry points, and along them, it's a high symmetry path that connects these two high symmetry points. And at the three regions, we have three different groups. Here we have a little group denoted as GK, right? And here we have another group denoted as GP. And in the middle, we have a smaller group. We denote it as H. So clearly, H should be a subgroup of GK and GP. And all the energy bands at the key point must form the irreducible representations of GK, right? And similarly, all the occupied bands must form irreducible representations of GP, and we denote them as rho and sigma respectively. And in the middle, they will reduce to a set of irreducible representations of the subgroup H. And for this band to be an insulator, all these levels must connect to each other. That means they must follow this condition. Rho 1 plus rho 2 reduced to H must equal to sigma 1 plus sigma 2 plus all the occupied levels reduced to H. They must form the same set of irreducible representation. Otherwise, some band must cross the Fermi level, connect to the higher band, connect to the connection bands, right? So in general, we will have this constraint. And even though this looks very complicated, but it turns out that the constraint they give for the B vector is very simple. All these constraints can be written in a similar form as this one we just talked about. So all these constraints turns out to be linear equations for the B vector. All these constraints we can write them in this form, in this simple form. So C is a matrix, and each row of this C matrix defines an equation for equation for this B vector. And if we collect all these compatibility relations together, we just have a very huge C-matrix, but still it's a simple linear equation. So given this constraint, we can define a set called the band structure set. We denote it as BS. It's given by B vector in the Z to the N. Here N is the length of the B vector. B belongs to Z to the N, and B satisfies this compatibility relation. So we can define this set. Basically, this is the collection of all possible band structures that follows compatibility relations, at least along the high symmetry lines. So roughly speaking, we can regard this set as the collection of band insulators. But it's a bit subtle is that this band structure may have some crossing point away from this high symmetry point, right? So there might be some topological same metals in this set, but let's for now forget about that. Let's say it's the collection of all the band insulators. So this is a first set we need to make use of. And we could also define another set called the atomic insulators. It's given by Pi times AI. P belong to Z to the M. Let me explain the notation. All these A vectors are the B vectors given by the band representation in real space. So basically, all these A vectors correspond to local orbitals in real space. Local orbitals, all band representation. And B is the integer coefficient. So if you can write a band structure as a summation of different local orbitals, we can regard it as a trivial, or we can regard it as the AI atomic insulator, right? So basically, band structure BS, this set defines all the possible gapped band structures, and this AI defines all the possible trivial insulators, right? So what's the non-trivial insulators? It's given by the quotient group between these two sets. It's obvious that this set is a abelian group, right? Because it's just like a lattice in some high dimension space, right? So we can define this quotient group as the symmetry-based indicators. So this is the general structure under the symmetry-based indicator. And if you run this algorithm for all the space groups, you obtain all the possible symmetry-based indicators, and then you can run the high throughput calculations to search topological materials, as Maya did and two other groups did. So this is the general structure for the symmetry-based indicator, and maybe I can give you a example for. Okay, maybe I can give you a concrete algorithm to show how this is done. So to show how this quotient group is done. Okay. So the first thing that is very important is that numerically people find that these two spaces have the same dimension. It means the dimension BS equals to dimension AI. So that means for every vector in the BS set, you can always write it as a linear combination from the basis in the AI set. But the question is whether this coefficient is fraction or integer, right? So basically, this is I don't know. I don't think this relation can be proven simply. I think it's just a numerical observation. So if you run this algorithm for all the space group, you observe this result. And so basically it tells us that for every B belongs BS, you can always write it in this form. Let me denote this as PI bar because I don't know PI bar is integer or not. I already use pi as an integer number, right? So we can always write a B vector in this form. So imagine that if we can choose a solution such that all this pi bar is integer, that basically tells us that this binding structure can be written as a summation of different atomic insulators. So basically that means it seems that it's trivial. So the statement is that if we have a B vector that we cannot find the integer solution, then this B vector must correspond to a topological state, right? So the general structure is to do this quotient group. Now let me explain how to do it. So imagine that given we already have a space group and we collect all the all the bundle representations together, and we define a EBR matrix in this way. Its first column is given by some EBR. Its second column is given by another EBR, and we put all the possible EBRs together to form a matrix. Okay, and so this equation can be put in this form: B equal to EBR times P bar. So, for simplicity, I just drop this overline. Okay, so now we try to find an integer solution for this P vector. This is a very complicated equation. I say it's complicated. It looks very simple, but I say it's complicated because these quantities are integer. So we have this integer constraint. So a very useful tool we can make use is the so-called Smith normal form. Through this Smith normal form decomposition, we can write so the statement is that for any integer valued matrix, you can always decompose it in this form, in this L lambda R form. And here, L is a n by n unimodular matrix. R is m by m unimodular matrix. Let me explain what this means. By unimodular matrix, it means that the L matrix itself is integer valued, and it's invertible, and its inversion is also integer valued matrix. So that's a definition of a unimodular matrix. So this is a very good property we can make use of. And the lambda matrix, it's n by m, but it's diagonal in this form. All the off-diagonal values are 0, and its diagonal values are integer. Okay, so this is a useful Smith normal form. So using this relation, we can write this equation in a equivalent form. Right? So now our target is to find an integer solution for P. And given that this, oh, sorry, I write it in wrong order. So our target is to find the integer solution for the P vector. And the good thing now is that R is a unimodular matrix. So if P is an integer vector, so will be RP. We denote it as Q, right? And so the problem becomes to find a solution of Q. Right? If we can find a solution of Q, then we can find the P as R to the -1 times Q, because R is a unimodular matrix. So so this property simplifies the problem. So the problem is simplified to this form, right? So we want to find the integer valued vector Q for this problem, and remember that this lambda has a diagonal form, and the diagonal elements are all integers. So let's consider if all these diagonal elements are just either 1 or 0, then that means we can always find a solution for Q, right? Because if this lambda is all integers, then we can simply solve Q as this. L to the -1 is still an integer valued matrix because L is unimodular, right? And L and lambda to the minus 1. So this notation is a bit subtle. This inverse should be called the pseudo-inverse. Right? Pseudo-inverse. You first transpose this matrix and put all the non-zero and replace all the non-zero elements by their inverse. So you can always have this solution if lambda is if the diagonal elements are all either 1 or 0, right? So, but imagine that if we have some non-identity elements for the lambda matrix, let's say lambda is just 1, 2, 0, 0, 0. If we have lambda in this form, that means it's possible to have a fractional Q vector such that, for example, in this form, such that B defined in this way is an integer, right? So if lambda has an element that is larger than 1, then it's possible that a fractional Q vector can give an integer B vector. That means for some B vector, it's possible to find so it's impossible to find an integer Q solution, but it's possible to find a fractional Q solution. So basically, we notice that these non-identity elements in the lambda matrix is very important. It's important for the topological classification. So after some, you can work this out yourself. It's very simple. So the conclusion is that the classification of symmetry-based indicators is simply given by this. Here R is the rank of the lambda matrix. So if all this lambda is identity, so you have Z1 is trivial, right? So you have this trivial classification. So if you have some non-identity, you have a non-trivial classification for symmetry indicators. And you can extract the expression for these symmetry indicators by looking at this L matrix. It's given by some columns or some rows of this L matrix. So basically, this is the general structure behind the symmetry-based indicator. I think I should stop here. I don't have time to explain the three-dimensional example. Maybe I can leave it to tomorrow. Mm-hmm.
Sure.
Mm-hmm.
Thank you. Perfect timing. So I'll open for questions.
Thank you very much for your talk. Is there any meaning behind like negative values for the P? Like I can imagine adding atomic installations.
This is a very interesting question. So so there are some reasons we can argue for the fact that we can neglect this thing. So the reason is that we can always put many enough bands below the valence bands, right? That won't change the topology of the system. All those bands are just, you can imagine all those bands as local orbitals, so that won't change the band. So even though your solution for P has some negative elements, you can always imagine that you have more bands below the valence bands. So in total, the P will be positive valued. So that's a justification for this method. But as shown as reviewed in this argument, the number of bands is very important to justify this. So if you can make a toy model where you only have a limited number of bands, this analysis might break down. So the violation for this theory is the so-called fragile topology. Sometimes you can find a solution for P with a negative value, but it cannot be realized in a model with a limited number of bands. It can only be realized with a model with more bands. So that's related to a fragile topology. Okay. Yeah. Thanks for this interesting question. Mm-hmm.
Thank you. In the previous page, I think you defined Q to be lambda to the -1, L -1, and B.
Right.
But lambda is a rectangular matrix, so I was wondering how do you invert it?
Yeah. So this lambda to the -1 is not the true inverse; it's the pseudo inverse. So the basically the pseudo inverse only guarantees. So let me put this explicitly. So basically, we want to solve this equation, right? We want to solve this equation, right? And let's see, lambda only has 2 non-zero elements. All the other are zeros. It's not a square matrix, it's a rectangular matrix, right? And Q1, Q2. And we know that there must be a solution for Q. This is proven by brute force enumeration for all the space groups. So we know there must be a solution. So this state means that we can always choose a solution where Q3, starting from Q3, all the elements are 0, because we know the solution exists, right? And so we can always write the solution as Q1 equal to 1 over minus 1 L times B, and the first row, right? The first component, and the Q2 as 1 over lambda 2, right? And the Q3 equal to 0, Q4 equal to 0, right? We can always define the solution in this way. So basically, this is what I mean by the inverse. It's not the true inverse of a matrix.
Yeah. Thank you very much for the nice talk. At some point, I get a little bit lost, and I want first to ask something. This EVR, that what probably is elementary basis representation or something like that. I don't know exactly what it means, EVR. Okay. That refers to these real space functions that you were talking at the beginning, like how that is that the real space representation?
Yeah, basically EBR is just you can understand EBR as the local orbitals in real space.
Okay. Yeah. Do you assume at any time that you have like a one-to-one relation between the way the number of local orbitals and the way they transform? Because you can have, usually in real life, let's say you can have atomic orbitals, for example, that represent with respect to some symmetry operations in the same way, but they are different. Like it could be as an S orbital and a PC orbital in graphene. Is that a problem for this integer only or not?
Yeah, in this framework, those orbitals will be regarded as the same, because as long as two orbitals will be regarded as the same as long as they transform in the same way and the symmetry group. So, for example, if we only have inversions, then we will say S and D are the same orbital because they are both even under the inversion. Yeah, so we do not distinguish this quantitative difference that cannot be known from the symmetry character.
So you imagine that there is some like linear combination that makes the job for whatever you have to need there or something.
What was
I wonder if in fact, in some cases, you might need to take both orbitals, for example, S and PC into account, and then this could be a problem, for example, for this condition that P has to be integer and cannot be. I wonder.
Yeah, I think the algorithm can be expressed in the following. So we can consider the atomic orbitals one by one. So we start from S and then P, and we examine whether P and S form the same representation. If not, then we add P, and then we consider D, right? And we examine whether it forms a new representation, and we continue this process until all the representations are realized, right? Then we stop. Then that's enough for this for the analysis under this framework.
Okay. Yeah. Thank you.
Yeah.
Maybe one quick question.
So you said that. So you showed this stuff for inversion, but so has someone done this for like other discrete symmetries, like C4 or whatever?
Oh yeah. This is already done for all the space groups and all the magnetic space groups. Yeah.
I see.
Yeah.
Okay. Yeah. Thank you.
Yeah, it's in the paper by Andrei Bonovig and the paper by Vishvanas. Yeah.
Let's thank again speaker.
Okay.